Hi guys, good evening. Good evening. And welcome to the end of the week. My name's Paul, I'll be your host on this wonderful mathematical show. Wrap the week up with a bang. It's the highlight of your day. You've been going through the motions, breakfast, lunch, supper, and you're well fueled. You are ready for exponential decay. I feel it. I do feel it. Exponential modelling of some description and then a cheeky bit of integration and we should be good to go. Anything to say? Announcement, major news alert. I can't do 5 PM next week. So we're back to 10 AM. Alright? 10 AM next week. And also I think I'm just going to do one more week of the lives for now. One more week of live maths. And then a temporary break because I want to focus on getting some topic videos done for YouTube. So yeah, I really want to do that. Get it in a more slightly more slicker, professional Hollywood style topic videos. So, but I will do one more week of these at least. Then let's pause it and I'll focus on that, and we'll come back and reassess the situation. Anything else to say? Let's just try these together. That's it, really. Let's get in there. You know, you probably were, you've been relaxing the rest of the week up till now, up till Thursday. You've just been sitting on the sofa, but now it's come to Friday. I think now is the time for you to actually get in there with a pen and do it with me. I'm going. Don't know about you. You might have already started. Science experiments, grams, minutes. Writing something down. (300) e to the minus 0.05t. I mean, by the way, you might not have obtained your coaching badge to be able to know what this graph looks like. And actually, maybe I did it slightly wrong. We should probably cut the m-axis at some point. But that's all right. For a general shape, it's an exponential graph to a negative power, and so it's going to be curving down that way. It might actually cut like that or something. But that's the kind of general vibe. A normal exponential graph looks like that. This is just kind of backstory, really. This is the prequel to this the Hollywood blockbuster that's about to ensue. That is a, well, I should label the coordinates. That's just a general y equal y and x exponential graph. This is when it's e to the negative power. It's like a transformation f of negative x, so it'll flip it like that on the y-axis. Anyway, no one cares. No one actually cares about that. Find the time taken for the mass to decrease to half of its original value. Well, so something is decaying. If I put in the time here, it's going to give me out its mass. So if you're looking at this model, even the dotted line one, you know, if I just plug in the time, it's going down the way. It's going to have some initial value there. The initial value is t equals 0. And at t equals 0, you've got 300 e to the 0. E to the 0, his maiden name was 1. Anything to the power of 0 is 1. So the starting was just 300. So really, for this question, what we're trying to solve is 150 equals 300 e to the minus 0.05t. Mildly croaky voice today. Probably could do with some coffee. Yeah, I have actually graduated. I used to teach mathematical potions at Hogwarts, third year, but had a bit of a fall in with some of the staff there, so I have had to resign. Anyway. So that's happening. That's a half equals e to the minus 0.05t. Now, how are your log skills? Have you done them? Did you do them in AS level? Have you forgotten them since then? Did the schools get cancelled this year so you didn't get a chance to revise them? Log both sides. And I'm just going to do it in one step because that immediately has that effect. If you take the natural log of both sides, and therefore 1.5 over minus 0.05 equals t. You know, if this is a bit fast, you've always got the turbo recap. It's going to be there, come rain, shine, hell or high water. I'd say, yeah, not sure if high water should be directly comparable to hell. It doesn't seem like high water would be such a bad thing. If hell was the alternative, that's something for philosophy class. Here, I would say that. And what we're dealing with, is it in minutes? So that's the time, okay. Find the time taken for the mass to decrease to half its original value. Turbo recap. Thrown at us like a snowball. Exponential snowball with ever increasing radius. Question was asked, how long does it take for this thing to half? Well, I just drew you a rough graph of what this thing could look like. There's a few different ones. I don't know. It depends what the numbers here are, right? Maybe that's what these different ones I drew on were. That's probably shouldn't have done that. Anyway, can't go back. You get the idea. It's dipping down like that exponentially. Positive exponential one would be going up the way. Case in point. What else to say? Yeah. Let's find out what it was at the start. T equals 0, plug it in. You get 300. After convincing yourself that e to the power 0 is 1. And so you got 300. Well, half of that's 150. So why don't we just plug in 150 on the left-hand side and try and solve it. That's what we did. Divided 300 give us a half. Then this step here is really worth, just making sure you're convinced on how to do that. To undo an exponential, you do natural log. So if you do that to both sides, your left-hand side becomes natural log of a half, and your right-hand side, well, it undoes the exponential, and you get that. And that's just solving. There's the time it takes for it to half, and actually, all you computer game players from circa 2001 will be very familiar with Half-Life, which is what this is. And if you didn't do that and don't know what I'm talking about, then that's probably better. Actually, it's probably better for your sanity and sort of respect. But this is the nuclear thing, right? So it happens in physics, it happens in chemistry. You got this word half-life. How long does it take for substance's radioactivity to half? So it started off being, 300, went to 150 in 13.9, so it's like the half-life of the material. Continuing, I took quite a long over a 3-mark question. How are we going to get through this? I'm going to have to really stop talking and start writing. It is that coffee has done it for me, I think. Shouldn't be allowed to drink coffee past 10 a.m. Find the time when both substances are... Okay, so there's a new substance. Let's call it N. This time it was initially 400. So let's write it like that. E to the something times t. When you've got these exponentials, the number at the front is the initial time. Or is the initial mass, I should say. Just based on the fact that when you put in the t equals 0, this whole expression on the right goes to 1. And so it's always going to be, this thing at the front is the initial mass. So okay, Then we're going to plug in what they tell us. They're saying that, oh, after 10 minutes it was 320, okay? So 320 equals 400 times e to the, just swap them round, 10b. See what I'm doing? I need to find b. I'm continuing. E to the 10b like that. And let's just do it to emphasize again. This is exactly the same move as last time. Bit of a weird way of it, but I'm going to have to now take, to undo that exponential, I'll take natural log of both sides. So the left-hand side becomes ln 320 over 400. That could probably be simplified. That'll be 10b on that side. So b should be ln of 320 over 400 divided by 10. I'm going. So I'm hearing, oh, I need to divide that by 10. Can divide it by 10? Yeah, that looks good. Minus 0.0223. Let's go with that. So our next model, or the second one, I guess it's a different substance, right? Yeah, second substance. So that's good. So it's almost like the accidental error that I made at the start. It wasn't even a very nice graph, but it's almost like it was worth it. I'm not going to draw it again because once bitten, twice shy, but this is a slightly different slope. Different substance decreasing at a different rate. So we got 400 times e to the minus 0.0223. And just to rewrite the first one, that was m equals 300 times e to the minus 0.05t. Like that. I'll recap that at the end. I'm not going to recap now. I'm just going to keep going. So I managed to use the data to get an equation for the other thing. I'm seeing the word. I'm seeing the word rate. Yeah, I'm seeing the word rate. I'm differentiating with respect to time. If I am seeing the word rate, what rate something going at? I don't know, the rate of your running, the rate of your heart rate. I don't know. I didn't work out a differential equation for my heart rate before. That's something that lies ahead of me. But anyway, if I hear the word rate, any kind of change of something, how fast a volume is leaking out of a container, the rate at which it's going out, it's going to be a time derivative. So dn by dt, and I'm also doing dm by dt. And yeah, they're saying when they're decaying at the same rate. So I guess let's just do it first, and then I'll show you what I'm going to do. Differentiating these. So the rule with exponential is, just in case we don't know that, if it's got the simple structure with numbers, then if it's y equals e to the 2x, the derivative is 2e to the 2x. Definitely quite a lag in the video today, it seems like. I'm not sure if there's much I can do about it. It does seem to eventually catch up, but it's a bit like a horse race. So I'm just going to keep going, okay? Yeah, so derivative of e to the 2x is 2e to the 2x. So basically when you're differentiating, you just have to multiply the number down the front. So for that first one, I'm going to do minus 0.0223 times 400. And then down the front of that one, then you'll have minus 8.92 e to the minus 0.0223t. And on the bottom one, 0.05 times 200 is 15. So minus 15 e to the minus 0.05t. Let's just do a bit of a circle around that. So yeah, you've got your original equations, you've differentiated them, and now you've got to set them equal to each other. So I'm just going to keep going. and I will recap it all afterwards. I'm setting them equal. Yeah, not much I can do. Setting them equal, times by -1 both sides, and you can end up with, what's the best way to do this? You could end up with e to the minus 0.0223t equals 15 over 8.92 e to the minus 0.05t. Okay? Log both sides. Or actually, no, I'm going to do something else. This is where you could log both sides. And let me just do 15 divided by 8.92 first. Then you get 1.68. This is probably one of the more exciting tricks in the book. If you've got an exponential at both sides, and it's negative like that, I'm just going to do it and then maybe try and justify it afterwards. I'm going to times both sides by e to the plus 0.05t times plus e to the 0.05t to both sides. Now, so the beauty about that is if I do it to the right hand side, then it just becomes 1.68. Because the exponential, if you multiply powers, well, if you multiply two things, the powers add. You know, if you did x squared plus x cubed, it's x to the 5. In the same way here, e to the minus 0.05t times e to the 0.05t, you add the powers, so which gets to 0, and anyway it cancels like that. So that's a nice little trick to have in your book. Similarly with the other one then, you're going from minus 0.0223 plus 0.05, and you'll end up with e to the 0.0277. So maybe you see why I did that now. I mean, you could have logged it earlier, but it's just, it looks a lot nicer now, and now I can just natural log it. I missed a t somewhere, haven't I? There you go. So t should equal that, ln 1.68 over 0.0277. Let's check it, and then we're going back. Divided by 0.0277, looks good. T equals 18.7 minutes. Okay. You might have to go back and watch it, or check this video later or something, and I don't know, somehow try it yourself and piece it together. This is some sort of extra Mensa accredited puzzle that I'm making for you. The video is not in time with the sound. But anyway, I'm doing my turbo recap, and hopefully you can get a flavour for what's going on, even if you can't see it totally. They have said there's a second substance, and it's got a different rate of decay. They gave us the first one, we had to work out the second one. Now, immediately they told us it was initially 400, so I knew it's got to be 400 times e to the something, because the number is the initial rate. You know, convince yourself of that. T is 0, and it falls into place. Then to find what b is, because the equivalent in section 1, b is minus 0.05, well, this time we had to plug in numbers. We had to plug in 320 and 10, solve it with a bit of logs, and we ended up with our b. Then once we had the equation, we had to differentiate both of our things. We had to differentiate them because it asks when the rates are equal. Rate means time derivative. Differential and exponential, fortunately, not too traumatic. You just have to multiply the number down the. If it's a more complicated exponential, there is an actual technique for it, and there are rules. And actually, spoiler alert, it's basically chain rule you're doing. It's basically chain rule, but for our purposes now, all we need to really think about and know is you multiply the number at the top down the front. So here you're multiplying the minus 0.05 down the front. Same with the other one. Get the derivative. Okay, set them equal to each other. And then it's basically a question of, can you do your log algebra? Can you multiply or somehow divide or log it correctly to get t equals? You really want to make t the subject. And the only little other thing I'll just to re-mention is that little trick where we got to some point where we had e to the minus power on both sides. We had e to the minus power, and instead of doing absolutely mad stuff, I just thought, let's times both sides by the bigger power one. So that's actually the minus 0. Well, you could do either, I guess. You could do either, but choose one of them, multiply it by the opposite. So I times by 0.05t, and it had the beautiful, look at that, it's like a game of chess or something. Almost like checkmate. Just takes it from something complicated into something a lot more beautiful, and then you can solve it more easily after that. So that's a good move to remember, and the rest we're just plugging it in. Okay, I'm going to move on to integration question. Let's see if we can do this some sort of monstrous rate of knots. I'm actually going to, should I just, okay, I'm going to try and maybe stop. Should I try and stop this streaming and going again to make it catch up? No, I'm just going to keep going, alright, because it's probably going to make things worse. So instead I can just kind of, well, hopefully you can see the graph there. We can just kind of talk about it a bit as well. It's got exponentials. It's got exponentials featured there. So they're here to stay. And actually, if someone hadn't drawn that graph and it just said 2e to the 2x minus xe to the 2x, you might have been shocked, to be honest. You may have passed out. I don't know. Does 999 cover this kind of thing? I'm not sure. But at least they gave us what it looked like. I mean, that is not a normal graph that you're going to see in A level. It's not like quadratic or cubic or sine, cosine, any of this kind of thing. It is pretty extreme. But that's all right. We don't really need to know much about the behavior. We just need to know how to integrate. Because they want this area R, and as we've talked about before, as I've mentioned, and let's get used to the idea, is area under a graph. That's how you get the job done. All right. So really, this is the integral of the whole thing to e. So it's the way to get our answer. Could even write area equals the integral 2e to the 2x minus x, blah, blah, blah. The only issue, well, there's going to be a couple of other issues that crop up, but the only initial issue to discuss is what are the boundaries, or the what other words do you call them again? I always forget what the actual nice words are. The limits. Send me answers in a postcard for what you actually call these things, top and bottom. I'm going to stick with boundaries. Okay, the first one is 0, because it's these things that we're looking for. These are the boundaries. It's the x coordinates. So the left-hand x coordinate of this thing, I can see from the picture, is 0. No questions asked. So that's fine. Just need to get the right-hand place where it cuts the x-axis for the boundary. And to get that, well, y equals 0 for x-axis points. Alright, so we can just set our thing equal to 0. 0 equals 2e to the 2x minus xe to the 2x. Yeah, so I'm just basically setting the y equals 0 and solving it. And yeah, no, this is another little thingy. I'm going to do it and then do a mild rant. take out a common factor. Don't start cancelling things. Don't start dividing by e to the 2x. You might get lucky. You might get lucky and get the answer. All right, it has happened. I remember it must have been 1964, January. It was a very cold day, and it did once happen. But as a guiding principle, factorize your stuff if it's 0 equals, because you might miss a solution if you start dividing by x or whatever. And okay, I could give examples, but then now's not the time. We're already going to be over time and distracted. So what I'm saying to you is so 0 equals 2e to the 2x minus x times e to the 2x. Factorize, pull out an e to the 2x, and so you're left with e to the 2x brackets 2 minus x. And then, so either that is 0 or that is 0. Now, e to the 2x can never be 0, because try it actually. Why don't you do that? Why don't you try and plug in something for x in e to the 2x, which gets you 0. Alright, and I don't want you to come back to me until you find something. That is quite a sentence I've just dished out on you. It doesn't work. The exponential graph never touches. Anyway, basically, the only solution you can get from that is x equals 2. So that tells you that our top boundary is 2. So we've actually, I can see, you know what, let's try and at least rejig this a bit so the paper's on there. Let's try that. See how we're going. Right, but ultimately we've got our integral now. We need to integrate between 0 and 2, the whole function basically. I'm going to go for it. Minus now, the reason I've split it up like that into 2 is because the first term, 2e to the 2x, that's reasonably easy to integrate. The second part is not easy to integrate, but it's integration by parts. And this is something we didn't cover yet on the live videos. We've done substitution. I think we did a little partial fraction in the first one. This is the last main integration rule, and it's integration by parts. And I need to spot it, because in that second term, it's got x times e to the 2x. So you've got two things multiplied like that. You've got two functions, a u and a v, if you like. And sorry, I'm just distracted trying to get it in line. Yeah, that's how you notice if it's two things multiplied in that style. So I'll write out the rule first. Integral of u v dash equals u v minus integral of u dash v. In a box. U equals x. And v equals e to the 2x. In fact, no, it's not v, sorry, it's v dash. Notation from yesterday, if I put a dash, it just means a derivative, just like f dashed x. I could write that out as du by dx and dv by dx, but ink saver's anonymous. So you integrate that. Now, what's the integral of e to the 2x? Someone, think about it. Think about e to the 2x. I've told you if you differentiate, the 2 comes down the front. If I'm integrating, it's going to be a half e to the 2x. That's the integral. And the derivative of u is 1. Of x is 1, sorry. So get all those things. Now I just need to plug it in. U times v is going to be a half x e to the 2x minus integral of u dash v, which is just going to be a half e to the 2x. And that's it basically. And actually, I could now integrate the second part of that. So yeah, sorry, it might be a bit confusing if you can't see exactly where I am with this, but maybe the words will help you to, maybe if you write down the words I'm saying and then you can cross-check it when the actual image becomes clear. In a way it's good, it encourages you to be there with your pen and paper writing it. A quarter e to the 2x. And you can check that by going backwards. Integral of a half e to the 2x is a quarter e to the 2x. Because if you're differentiating it, you would multiply a 2 down the front, you'd get 2 over 4, which is a half. So that works okay. And, alright, let's just all put this section is kind of separate. Going back to the main integral of that is just, of the first part, is, what's it going to be? E to the 2x. Right, yeah, that's right. Minus all that stuff we've got from down there, a half x e to the 2x, minus a quarter e to the 2x, between 0 and 2. And just write it out again at the top here, and then do a bit of a recap of what I've done. I'll try and do it without reference to the page and just talking through it. And you'll see it on the page in due course. Okay, so basically, what are we saying? Find the area. So that amounts to integrate. I need to integrate between the places where it hits the, or where the area is bounded like this on the x-axis, like bookends. So on your left-hand bookend, you've got x equals 0. On your right hand, you're going to have to work out where it cuts the axis. Luckily, I know the y-coordinate of that. It's y equals 0. I can plug that in, factorize it a little bit, and notice that it's got to be x equals 2. And you can just double check it, plug in x equals 2, and check, does that stick out y equals 0? That would be a way to double check it. So we got the 2, next we need to integrate. Two terms there. First term is okay. Now, maybe if you've not come across differentiating or integrating exponentials, that's alright, don't panic. It's not too bad. And I told you the rough idea of how to do it, but yeah, you'll sit down for 10-15 minutes with your children and read it and sort of do it with them as a means of bedtime story, getting them to fall asleep. But it won't take you long to get there for that first term. The second term looks similar. Unfortunately, there's an x times out the front. So you're not going to easily get that integrated. In fact, if anything, that's a classic by parts. So if you are in A-level year 13, you should be looking at that thinking, I know that's integration by parts. It's not a substitution. You could maybe do it by substitution as well, but it's not naturally substitution. It's not partial fractions. It's not really reverse chain ruler. There's nothing much else it is. You've got two things multiplied. One of them's easy to differentiate. One of them's easy to integrate. It's integration by parts. The rule's there. I've written the rule out there. So yeah, if you're just looking at it actually, uv dash. So yeah, your first thing is you're going to differentiate it. That's the u. And the v dash, so that's already the derivative, you're going to integrate that. So that's what I did there. I differentiated the x and integrated the e to the 2x. And then I literally just plugged it into the formula. Think about the integration by parts formula, which is a bit different to like the differentiation formulas and this kind of thing. You've got another integral to do. You see that? You see that? Integral of uv dash equals uv minus integral of u dash v. So look, it's not like, here's a rule for integration, just spits it out. We should be so lucky. If anything, you just get a second integral coming. The point is, it's an easier integral. And this time it was. Once we did that rule, The actual second thing we had to do was easier. It was just a standard e to the 2x one. Didn't have that x multiplied at the front, so we could do it. All right, so that might be something you're thinking. You might be just absolutely shocked to the core that it's still an extra integral you have to do within the integration by parts rule. But that's the sort of art of it. It's making sure you set it up so it's the second integral is easier. Okay, I'm continuing. Yeah, so we've got here, and now it's just a case of plugging it in, basically. So you're going to have e to the 4. Oh, why did I change pens? I'm not totally sure about that one. E to the 4 minus a half times 2 times e to the 4 plus a quarter e to the 4. So that's that. And then if you put in 0, you get e to the 0 minus, well, actually that second term is just going to go to 0, because when you put in x is 0, then you get the 0. What else? Minus and a minus is plus, so you've got, yeah, this is where you could easily have got the rest of it done well and still stuff it up with these signs here, so I'm just trying my best not to. Minus is plus, so it should be plus a quarter e to the 0. Wow, so let's just tidy that up a little bit. So that looks like then e to the 4 minus, well actually I've got e to the, that seems a bit dodgy, do I do something a bit wrong? Wait a second. Good. Let's go with it. Minus e to the 4 plus a quarter e to the 4 minus, since that's e to the 0, that should be 1. And then you'll also have minus a quarter, it looks like. Yeah. So it looks like then you'll get a quarter e to the 4 minus 5 over 4. Sorry, that was mildly painful just having to watch me do algebra, but it's exactly this kind of thing in the integration. The last couple of steps, not putting in your calculator, practicing not putting it in your calculator, practicing plugging the numbers in correctly and keeping it as e, keeping it as an e to the power, keeping it as a log to the power or a log to the base, whatever. But I'm pretty happy that I got that out in the end, fine. So yeah, I already did the major recap of it. I don't think I need to say too much else. And that's just your standard plugging in the 2 for x at the end and plugging in the 0 and subtracting them from each other. So when x is 2, and then plug it all in and subtract x is 0. X is 0. Remembering something to the power 0 is 1, blah blah blah, and it all falls out. Okay, fine. Maybe I'll just witter on a little bit while that video catches up to finish off. Oh, it's almost there. Welcome. Quarter e to the 4 minus 5 over 4. I think that's what we're dealing with. Thanks, guys. Bit of exponential manipulation. Liking that. Exponential modelling, that first question we did, that kind of thing comes up a lot in all the exam boards, especially OCR, EdXL. They love a bit of that, so it's good to get into the hang of manipulating exponentials and logs. Have a lovely weekend. Back in action next week, 10 AM. And any questions or anything, let me know. Follow me on Instagram, give me some chat there, see what's happening. If you're holding any maths parties at the weekend, please, online maths parties, please do invite me. I'll happily attend. Otherwise, catch you guys later. Thank you. Bye-bye.